I'm pleased to introduce Michael Carbin, who's coming to us from MIT. We are, just like we are approaching the end of our interview season, we are at the end of his academic interviews, and he's very pleased to be here. So he's going to talk to us today about approximate computing and reasoning about approximate programs.
Thank you for that introduction. So today I am going to talk about approximate computing, and I think actually here of all the places I've been to, there's perhaps some familiarity already with what approximate computing means. But the way I like to introduce this concept of approximate computing is through a thought experiment. And that thought experiment is, imagine if I were to give you a compiler that's going to apply the following transformation to your program. So this transformation is called loop perforation. And what it's going to do is it's going to find loops in your program and transform them so that they execute for fewer iterations. And the thought experiment is, what will happen to your program? Well, what was that? Didn't hear that one. Yeah, well, actually, no. If you're actually from the approximate computing community, the first thing that comes to your mind is, this is amazing, right? My program's going to be faster. It's going to consume less energy. Like, maybe, we're doing less work here. Maybe we should do this all the time. But, as you pointed out, when we tell people this, they say, you're crazy, right? Your program may give the wrong result. But that's not true. In fact, what you'll just get is a different result. And the real question is, just how different is that result? Because if we can bound how different that result is, then we can perhaps make your program faster, consume less energy, and still be acceptable for your needs. So that's what I'm going to talk about today, are some techniques for doing exactly just this. But to continue on with this experiment, this thought experiment, let's actually go ahead and just try this transformation out. And what I have here on this slide is a single video that's gone through 2 versions of the X264 video encoder. So this version on the left has gone through the standard X264 video encoder, whereas the version on the right has gone through a version where we've had a system that's gone in and found places where it is profitable to transform some loops to trade accuracy for increased performance. So essentially to transform them, make them execute for fewer iterations. Now,
why isn't it tractable be twice as fast?
So I think it depends on when these 2 threads get started. But here, so as you can see, there's some minor differences between the quality of these 2 videos. But the major difference between these 2 videos is the video on the right is encoded 2 times more quickly than the video on the left. Now, the way this system works, and it not only works for something like video processing or media processing, we've applied this sort of system to things like search and finance and machine learning and vision. And the way this system works, so this is work that I've had that's gone on in my group, and the projects highlighted in green are projects where I've had the privilege to participate. And the way this system works is essentially a developer can give you a metric that compares the quality of the result of a standard vanilla implementation of the application. And then it'll also compare and compute the difference of a result if it's gone through our perforation framework. And what our system will do is use that metric and abound on how much accuracy this developer is willing to tolerate, accuracy change this developer is willing to tolerate, and identify loops where it's profitable to actually get a performance boost for trading some change in the accuracy of the program. Now, what we've seen when we applied this system to these sorts of benchmarks is that we typically get a factor of 2 performance improvement, sometimes up to a factor of 7. This all comes with about less than 10% change in the quality of the output. Now, the reason why this sort of system works is that these applications here are coming from these domains of what we call approximate computations, in the sense that there is a very natural trade-off between the quality of results that these applications produce and the time or resources or cost that it takes to compute those results. So this trade-off space gives us this opportunity now to change the behavior of the application so that it can trade quality of results for increased performance. Now, inspired by this, people in our group and in our community at large, including people here at University of Washington, at UW, have actually looked at a variety of different techniques for approximating components in your application. So we've seen this code perforation example. But people have also looked at mechanisms like function substitution, where I have a function in my program, and I'm going to substitute it with an approximate implementation, for example, something that's implemented with a neural network, for example. We've also seen techniques like relaxed synchronization, where we have large parallel applications that have locking operations in them, but we'll build systems that come in and remove some of those locks, therefore increasing parallelism, but introducing data races and therefore changing the quality of the application's results. And again, people in both, another interesting thing is people in both the academic and industry hardware communities are starting to consider ways of building hardware where itself may produce incorrect results with some non-negligible probability. And again, some of that has been going on here. Now, what all these techniques do is they take this original application in this trade-off space, and now they create these new points where we can move our application so that it can deliver the appropriate performance given the context at hand. Now, going back to the original thought experiment, right? The reason why people get scared about this and what's going to happen to my program is that they're asking really, how can we reason about these approximate programs that are going on? It's great that we can do this and get this performance benefit, but I need to have some confidence in what my program is doing. And the problem is that not only may your program produce a wrong or inaccurate result, it could just produce a completely invalid result that doesn't make any sense, or perhaps crash, or do something generally nefarious that we weren't expecting it to do. And now to address these problems are a variety of different fundamental challenges that we need to think about, particularly how do we express important properties that our developers want to be true of these applications? How do we think about the semantics of approximation, of changing the behaviors of the program? And finally, how can we reason? How can we actually build confidence or verify these applications? Because if we just do our standard technique of doing code review or testing, this can be really difficult to debug. Right? We may find bugs in our application, and we have no idea if this is coming from the fact that we've applied these approximations or whether or not they exist in the application before. And then also, right, if we were to do standard verification here, assuming that we were to verify our program to begin with, here we'd have to redo a lot of that proof, and there may be a lot of burden going in to try to do that verification. But what I'm going to talk about today are some contributions that we had in building foundations for solving and addressing some of these problems. So specifically, I'm going to talk about a program logic and verification system for verifying safety. Whether or not our programs are producing valid results, that they're actually not doing malicious things. Then going to talk about a program analysis for verifying reliability. So this is going to be the probability that our program produces a correct result. And then finally, I'm going to talk about how these systems actually make it possible to talk about accuracy. It's actually putting bounds on the results that these applications produce. So now, the first system that I want to talk about is this program logic and verification system. This is work that we had a couple years ago in Ph.D, and this is work that I did with my grad student colleagues and my advisor. And the main goal of this work was to figure out a way to how we could represent approximate programs and efficiently specify and verify safety properties about these programs. And in that course, provide a logic and verification system for doing so. Now, to make this all more concrete, I want to work with a concrete example. And that example I'm going to work with is image scaling. We're taking this image on the left, and we're going to scale it up to produce this image on the right. Now, a common way to implement image scaling is with a kernel called interpolation. And the way interpolation works is that for any pixel in my scaled up image, I'm going to map that back to a neighborhood of pixels in my original image. I'm then going to take some function or average of that neighborhood, and then I'm going to set that value, I'm going to take that average and set it to be the value of my pixel in my scaled up image. Now, one way of implementing this, a very simple way of implementing this, is with the following piece of code where we have this function interpolation that's going to take the coordinates x and y of a pixel in my destination image. We're then going to do this map step. We're going to max it back to a coordinate in my original image. We're then going to get that neighborhood in that original image. So here we're going to return n coordinate pairs in these arrays x's and y's. This will come from our get neighbors function. And then finally, we're going to average them together, or we're actually going to sum them up and then just average them together. So there are a variety of different ways you may implement image interpolation with a variety of different convolutional kernels, but this is a simple, straightforward way of doing it for the purpose of this demonstration. Now, the goal of this work is that now we have our example, and what we want to do is we want to take this single point in this application space. We're going to use and specify safety properties, so these safety properties that we're interested in, to put a bound or an envelope on the execution of our program. And then within that bound, we're going to relax its semantics using some primitives that we have for introducing new behaviors in our program. And finally, we're going to verify that this program still satisfies these properties that we have. So for the safety aspect, the safety of interpolation that I want to talk about here is going to be the safety of these array accesses that we have within inside of this loop. So here, what we're interested in is checking. So standard, we'd have these implicit assertions that we want our accesses to y's, source, and x's to actually be within the bounds of the array so that our application is not stepping outside of the bounds of the array or have memory safety issues. And here we've represented this with just a standard assertion. Right? This is something that you would see in a standard programming language. And the way to read this assertion here is that we're checking to see that our coordinate y's, this y's of y, is actually within the bounds of the length of source on this first dimension of source. So here, this predicate length of source 0 is going to be the length of source on this first dimension because we've got this rectangular array. Now, these assertions, of course, can represent a variety of different safety properties that you may think of, not only just memory safety, but we can also think about whether or not we're getting valid results, or whether or not we have results in a range, and also even more complex sanity checks that we may have on data structures. So now, given a set of safety properties that give us an execution envelope, we can go ahead and think about how to relax this program semantics. And the way that we've done this in this work is by introducing this new statement for relaxing the semantics of a program and introducing this approximation. And what it is called is this relax statement that I have here. So the way to read this relax statement is that I'm going to modify a set of variables non-deterministically subject to a constraint. So here the way to read this is I'm going to change the value of n so that its new value of n is less than or equal to the old value of n, where old value of n is going to refer to the value of n immediately before executing this statement. So here, when we think about this statement, the semantics of the statement, what it does is it introduces a perforation where we're going to truncate the execution of our loop and only look at a subset of our neighbors. Now, this predicate here is general, so we can actually express other different relaxations. So for example, we could think about skipping intermediate iterations, or we could have distortions, where we're distorting the values of values, or the value of variables in our program, which could represent something like doing function substitution, where we're putting in a different way of computing a value. And then also, you could do things like reconfiguration, where perhaps there are multiple ways of doing something in my function, and I'm going to dynamically choose, or I'm going to non-deterministically choose, which is an appropriate way to perform that task. Now, the thing about these relaxed statements is that they could be provided manually by developers, or you could provide this and explicitly notate where relaxation is possible in your program, or if you go back to the beginning of the talk, there's a system that we have. You could actually be added automatically. So an optimizer could go in using testing and that system we found before, find places where empirically we perhaps can apply loop perforation, and then generate one of these relaxed statements that represents how we could possibly and potentially change the behavior of this application and get a speed up. Now, what this relaxed statement does is it takes this original program, it's one point in our state, and again, it's going to introduce these new points. Right here for this relaxed statement, each value of n is a different point in this trade-off space. And in fact, this statement now gives us a family of programs, right, where if we verify this family of programs, right, all choices of n, then if we take this relaxed statement, this non-deterministic construct, and let's say that we have another pass in our compiler that specializes it to choose that n is equal to n over 2. Well, that is consistent with the predicate that we have in our relaxed statement. So that what that means is that if we verify this family, then we can have confidence that any consistent decision that we make at a later stage will also satisfy the properties for the program as a whole. So now, to verify this again, we're thinking about this safety. So the safety of these array accesses that we have here, in this case to y's in terms of length. And the thing to notice here is that if we wanted to verify this outright, right, if we wanted to just go and do a proof of the correctness of this new relaxed program, what you'd see is that if we wanted to do that, we'd really need to look backwards in the program. We'd actually need to verify that this getNeighbors function that we have, that we actually need to establish that all these coordinate pairs that we get are actually within inside the bounds of source. Right? And even more, if we wanted to establish that, we'd also need to establish that this original coordinate that we're choosing is going to be within inside the bounds of source. And what you can see is that although we've made this local change to the behavior of a program in the context of this loop, now we have to do this global reasoning and look backwards through our program, perhaps verify things. I mean, maybe we haven't verified this program, but perhaps we definitely haven't verified the semantics of these getNeighbors and these other functions that we're now being forced to reason about.
Isn't it just for differential verification or something like that? So basically assume that the original program was correct, and relaxed version also gives you the parent.
Yes, so there's an observation to be made here. It's a great observation. And that observation is that this length, right, this length of source that we have in here, right, isn't being modified. Even though we're changing the behavior of our program, this actually isn't being modified. And also, the contents of y's isn't modified. And what that means, it actually leads us to this, right, this observation, is we can come up with a new verification concept, which is, why don't we assume the validity of these assertions in the original program? Let's assume that our original program had been validated, right? This could be verification, any of the means. But now let's instead verify relations, right? Relationships between values in their original program and our changed program, right? And here, this relation that we want to verify is that the length of source and the contents of y are the same, right? That's a relationship between values in the original program, values in our relaxed or approximate program. And now using those relationships, we can now verify or leverage that fact to validate It's a relaxed program, right? Assuming that this assertion was true, and we haven't modified these variables in this assertion, for example, then we can demonstrate that, of course, that this assertion will be true afterwards. So now, if we do this verification approach and we go about verifying this, the way that we've designed this and implemented the system, you get the following theorems about what it means to verify a relaxed program. So specifically, we get this predication, right? If the original program satisfies all its assertions, then the relaxed program satisfies all its assertions. Again, remember, we're going to verify just these relationships and assume that our original program satisfies these assertions. Now, what's important about this and what's actually nice about this when you think about it is that this first part can be established through any means, right? So it could be verification, but you don't need to verify that original program. This could be testing or code review. And this allows you to integrate with whatever workflow or whatever the way that you're thinking about verifying or validating this original program. Now, of course, we're making this assumption here. The good question is, what happens if this isn't true? What if these assertions are not true? Well, the property that we can get out of the system is that if the relaxed program violates an assertion, then the original program also violates an assertion. Now, what's important about this is that you can observe now that if there's some bug in the relaxed program, then there must also be a bug in the original program. So if I want to do debugging and think about perhaps invalid behaviors that are showing up in my relaxed or approximate program, then I only need to debug with that original program, and I can do just that reasoning there and not have to think about this relaxation that was going through. So now that gives us an approach, right? An approach with some theorems we can think about for verifying these properties. And here, what we want to do, if we want to implement this process, we really need a formal system. We need a formal system and a logic for verifying these observations that we made. Now, typically coming from the programming languages community, when we think of verification and logics, we typically think of the standard Hoare logic. And what the standard Hoare logic is this notation that we have here, which is this turnstile P, S, or turnstile P, curly braces P, S, curly braces Q. And what this S is, it's going to be a statement or some sequence of statements, like the body of this function that we have here. And now these P's and Q's, they're going to be predicates, right? They're going to be predicates over variables of values of variables in our program state. So I could say, x is greater than 0, for example. Now, what this notation means is as follows. It means Hoare logic is essentially a sequence of rules that allow you to define the following. You can say if some precondition P is true before the execution of S, then some postcondition Q is true afterwards. Now, what Hoare logic is a set of rules that allow you to prove arbitrarily complicated P's and Q's. But here, a simple example is that, well, if I know that x is greater than 0 and I execute y is equal to x plus 1, then I can verify that y is going to be greater than 0. Now, in the standard Hoare logic, right, the standard Hoare logic, again, exists of a number of rules. But if we wanted to verify an assertion, a way that we would express this is with an inference rule that looks like as follows. Now, inference rules can be kind of scary sometimes, but this isn't so bad. So the way to read an inference rule is that above the line, we have a premise, where if we can establish the premise, we can conclude what's below the line. And the way that you would use this rule in this Hoare logic is you can imagine using some other set of rules. I'd be stepping forward through my program, building properties and facts about the semantics of my program, and I would hit an assertion that I wanted to verify. So when I was stepping forward, I would build this precondition. These facts would come into this precondition P. And if P entails my condition B, then this assertion is true. I know that all dynamic executions of the program are going to satisfy this assertion. Then I could continue on verifying the rest of my program. Now, for example, if you wanted to verify that I is greater than or equal to 0, and let's say that I'm stepping through my program and I get to this assertion and I've been able to prove that I is greater than 1, then clearly I is greater than 1 entails that I is greater than or equal to 0. And I could continue on verifying my program with confidence that this assertion is true at this point in the program. So now that gives us this standard way of if we wanted to verify our program outright and we wanted to do all this global reasoning again, we could use that Hoare logic. But again, what we want to implement is this relational. We want to verify relationships. And the way we're going to do this is by modifying our Hoare logic to actually now refer to values in our original program and also our relaxed program. So here, what's going to change is the way that we're going to reference variables. Here is what we have colored, where we're going to say that this x angle bracket r is going to refer to the value of x in our relaxed program, in our approximate program. And our x angle bracket o is going to refer to the value of x in this original program. And now what we're going to provide is a sequence of rules that allows me to say, and the way our notation is going to change is that if some relation is true before the execution of s, I can prove that some relation q is true afterwards. So for example, if I can prove at some point that I know that x has the same value between the original program and my relaxed program, my original program, and I execute y is equal to x plus 1, then I also demonstrate I can prove that y will have the same value afterwards. So now using this change, we can go ahead and modify the way we're going to think about this assertion rule and implement our verification approach. So the first thing that we need to do is we need to ensure that we still need to ensure that this thing is true, so that this assertion is true in our relaxed program. And the way this is going to work is that now above this line, we're going to do this renaming of our condition. So this b angle bracket r is going to rename the values of the variables that we have in this condition to refer to values in our relaxed program. So here, again, if we're verifying that I is greater than or equal to 0, then I would rename this, and I get I in the relaxed program is greater than or equal to 0. And of course, if I wanted to implement now this standard verification approach, if I knew that I in the relaxed program is greater than 1, then of course that's going to entail that I in my relaxed program is greater than or equal to 0, and I could continue on verifying this program. But again, this is step 1. This is if we wanted to do the standard verification. But instead, remember, we want to leverage the fact that we can assume this property about the original program. And the way that's going to change is that now, for this entailment that we have, we're going to do this renaming of this value of our condition for our original program. So here, we're going to put that on the left side of our entailment. So here, what's going to happen is now when I see this rule, I can use this rule. I'm going to do this renaming where I know that I'm going to say that I'm going to assume that I is greater than or equal to 0 in my original program. And again, my goal is to verify that I is greater than or equal to 0 in our relaxed program. But now I can use these relations. Right? So for example, if I know that I in the relaxed program is greater than or equal to I in the original program, and I assume that I in the original program is greater than or equal to 0, then clearly I can demonstrate that I in my relaxed program is going to be greater than or equal to 0. I can continue on verifying my program. So now that gives you the formal basis for how we'd go about verifying, expressing these relations and verifying them. So we could take these observations that we made, that length and the contents of y's are not modified. Now we could express them formally. So here we could say that the length of source in my relaxed program on this first dimension is going to have the same value, length of source, in my original program on this first dimension. And then I could also say that for all values that I have in this y's array, it's going to be the same value in the relaxed program as it is in my original program. What's important here, right, is that we can see is like verifying these relationships, and they may not just be simple equivalences, but more complex relationships can be simpler than verifying these assertions outright, where I'd have to do and go and verify other components of my system. So now, to use our rules in the way that we would verify this program is we'd take our observations, we take our logic, and we can start at the beginning of our function and work down to reach this assertion. And the first thing that we would observe is that, well, all parameters, they have the same value in length. That's the first thing that we're going to know. Right? And we could express that formally, but that's not important right here. But what we would see is as we continued moving on through the program, right, we would see that all these values that we have are going to be the same between my original program and my relaxed program up until I hit this relaxed statement. Right? This is where the semantics of my program are going to change. Right here, before execution of this statement, I know that n has the same value between the original program and my relaxed program. And then in my relaxed program, right, I'm going to do this decrement. I'm going to decrease its value. And in my original program, I can just pretend that this doesn't exist. Essentially, my original program would not execute the statement. And what that means is that n in my relaxed program is going to be less than or equal to n in my original program. And of course, I could express that in my logic, and I want to keep that fact around, and then continue on towards assertion inside this loop. So now, of course, as we get down to this loop, going to have to reason about this loop, right? And reasoning about loops in programming languages, program analysis is always particularly challenging. And there's actually the interesting challenge here in this domain is that although these two programs, right, this original program and this approximate program, they share the same structure, right? They only differ by the addition of this relaxed statement. My original program and my relaxed program, these executions may start taking different paths through this structure. That really leads you to the question of how and when can you relate these two executions? Because, for example, if I have this control flow here where before perhaps they're at the same point, and then they're going to diverge, and then after they're going to come together, I really need to ask, what program point, when I write a relation, what program point am I talking about between the two programs? Now, for verifying this specific example that we have here, the observation to make on how this proof goes through is that this relaxed interpolation is always going to execute for fewer iterations, given by this fact that we have from our relaxed program. Right? This comes from this track, this fact that n in our relaxed program is going to be less than or equal to n in our original program. And what that means is if we were to think conceptually about taking these two executions, my original program, my relaxed program, and I execute them in lockstep together through all these iterations of the loop, I would see that at some point my relaxed program is going to terminate and my original program is going to continue on for the remainder of its execution. So from that observation, what we see is that the way you would verify this is that the accesses in my relaxed program are actually a subset of the accesses in my original program. And what it means is that these assertions, these invariants that we have along, we'd actually use this to discharge and be ensured that on every lockstep iteration of these two computations, that we can use this to assume that the assertion is true in the original program and demonstrate it's true in our relaxed program. Now, in general, the way that you want to think about this is that these relations are really well defined at these synchronization points. Right, so here, when we look back at this control flow, right, before we execute this control flow, we know we can match up the executions for our original program and our relaxed program. Then after they diverge, and when they come back together, again, we can match up the executions between the original program and the relaxed program. Now, the observation that we made while we were actually using the system and building it was that in many cases, some of these assertions that we're interested in are actually independent of the path conditions that we want to verify. And what our logic supports actually is verifying that these things are independent and actually moving these assertions to synchronization points, verifying there with those relations, and then pushing them back down to verify or discharge the assertion inside the particular branch where we encounter that assertion. So now that wraps up what we have with this particular project and this program logic. And the goals here, again, what we've been able to do is take transformations such as loop perforation and other things and make them a first-class member of our programming language. We can actually represent their semantics explicitly. And again, this allows us not only for a developer to communicate where relaxation may be possible, but even for an optimizer to come in or a compiler to come in and place these annotations on where it has found potential opportunities for relaxing the semantics of the program.
So what if your approximation involves, changing part of the algorithm that, there's no way to relate the two executions as closely as you're assuming you can here?
Mm-hmm.
Are you saying that essentially you're going to have to put the assertions go around the entire block that could change in your program, or?
No, yeah, for that one, so there what's been interesting is, so in that context, the real question is, if I have these different implementations, are there assertions inside that I can lift up? Essentially things that are going to be invariant that I can use to push down into a different example, right? So that's essentially the proof style that you would go through for trying to verify something like that, where you'd want to kind of harvest that information, pull it up, then try to do the verification and pull it down to another algorithm, if that's what you wanted to do. Now, so that gives us, so we've got these first-class transformations now. We've also got this verification approach where we can use the existing reasoning that we've done for our original program. Again, this could be testing, could be code review, whatever. We don't need to verify that original program, but we can still reuse the properties that we believe to be true about that original program to more efficiently verify this approximate or relaxed version of our program. And finally, we've got this logic, this programming logic that allows us to reason about the different concerns that come up while trying to do verification. Now, what this all comes together in is a big collection of inference rules, and this is a quarter of the inference rules or so. But the really important thing here is that we've taken these inference rules and actually translated them to Coq. And Coq is a proof assistant, interacting theory prover, that allows you to prove properties of a mathematical development. And here what we've done is we've taken these rules, translated them to Coq, and proved that our rules are sound with respect to the semantics of the programming language that we have underneath this. And what this means is that you can have high confidence that the judgments that are coming from our logic are actually sound and consistent with the semantics that we have. Now, another side effect or benefit from doing this in Coq is it also gives you a verification system. So you can actually sit down and interactively verify properties about a program. And the way this works in our system is that our system can translate these programs or fragments of programs through Coq's language. We'll then have the user can interactively use our rules, our logical rules, to verify these programs. And then Coq can check the validity of the proof so you can get a machine-checked verification of the properties that you're verifying for this particular program. Now, we've taken this system and we've applied it to a variety of different examples to verify properties about safety and even some more interesting properties themselves. Now, I want to switch gears a little bit. Yep.
Have you had any non-authors do these proofs?
No. I will not argue that they are easy. And it'd actually be great to talk about how you make this stuff more tractable. But actually bring that question up again at the end of the talk, because I'd really like to talk more about that. Yeah. So I want to switch gears a little bit and actually talk about verifying reliability for programs that execute on it's unreliable hardware. And I'll explain what that means in a second. But this is, again, work that we had very recently. And this was work done with my graduate student colleagues, my advisor, and actually some really awesome now first-year graduate students, actually maybe now second year, that came into this project. It's been great to work with them. So this unreliable hardware, what's going on here? And this is perhaps familiar to more than a few people in this audience. But what's been going on is, as I mentioned before, people in both the industry and academic communities are starting to consider ways of breaking this traditional digital abstraction that we've had to hardware. Digital in the sense that I have a chip or I have a CPU and I schedule instructions on it, and either it computes the correct result or it fails, and it's going to tell me that it's failed. And I'm going to be able to then detect that failure and do some sort of correction to recover from that. Right? And instead, what people are starting to consider are building hardware designs that look something like this, where they have both these standard reliable units, which are unshaded here, where you schedule instructions on these things and they do their normally expected behavior. But you may also have unreliable units. So you may have unreliable ALUs, for example, where schedule instruction 2 + 2 suddenly equals 6, right? Or I may have a memory where I write something into my memory, and when I read back from it later, I may not get the value that I originally wrote in. Now, when you tell people about this, again, it's another thing where they ask, why would you go build unreliable hardware when it's already hard enough to build reliable programs on reliable hardware, right? But here the motivation is that these components are going to be, these unreliable components are going to be faster, be smaller, and they're going to be lower power. And then for some specific budget, such as time or energy, I'll be able to get a lot more compute for that same budget. Now, of course, the challenge here is that once we go into this domain of approximate or some unreliable hardware, the real question is, what's going to happen to my programs when I start running them on here? And I want to go back to demonstrate this thought experience. Look again at interpolation. And here I'm going to simplify it a little bit in the sense that we're still going to have this map step. But now what I'm going to do is simplify this neighborhood. So we're going to look at 4 neighbors. So if I have a pixel here, I'm going to look at neighbors here and neighbors here. And of course, there are a variety of different ways of doing these stencils, but this is a way that leads to easier code to talk about. Now, once I have my neighborhood, again, I'm going to sum them up, and then I'm just going to average them together. Now, the question here, the thought experiment, is what happens if we have these pluses and multiplies be unreliable? Maybe they produce incorrect results with some probability. And also, what happens if these arrays that we have here, the source arrays, are going to be stored in these unreliable memories? Well, what you see is if you go and you simulate and you run this, and you plot the quality of our image scaling as a function of the reliability of our interpolation, therefore a function of the reliability of these operations that we have, what you can see is you get a variety of different results. And you can see that in some cases, you don't get acceptable results. And in fact, in many cases, you don't really get acceptable results unless, in these models, some of these models, the hardware is mostly reliable. So what that means, if you want to be able to have some confidence that you're getting accurate enough answers out of your application, you really need a little bit more than just this distinction between reliable and unreliable computation. In fact, you need additional information, right? So you need a hardware specification. It's going to tell you the probability that these operations execute correctly. I also need a software spec that tells me what's the required reliability of interpolation so that as a whole, I get a high quality or an acceptable quality scaled image. And then finally, I need an analysis, right? I need analysis coming from the program language standpoint. I need to provide an analysis that allows us to verify that this software, when executed on this hardware, will satisfy the specification and therefore allow you to get acceptable results. Now, of course, there are a number of fundamental challenges that you need to dip into if you really want to reason about these things, of thinking about what's the semantics of this hardware, the semantics of reliability, how do you reason about these things with logics. And all these things have been coming together in a system that we've been building called Rely. And again, it includes this hardware spec, the software spec, and also a static analysis that allows me to verify that software, when executed on that hardware, satisfies its spec. Now, the way these components work, and it's easy to start with this hardware specification, is that this hardware specification is going to list the unreliable operations that are available in my underlying hardware. So also with the probability with which each operation executes correctly. So one thing to note down here is we also have this named memory region URL where there are probabilities associated with both the success or the probability that reads execute correctly and writes execute correctly. And again, all these things can be reset. These are just example numbers that we've used based on the literature, but these can be provided in a number of different ways with different values. Now, one of the core assumptions here for starting and making this progress is that we're going to have each of the failures of the operations actually be independent. And we're also going to allow these operations to produce arbitrarily incorrect results. So we're not going to try to reason about the distributions of errors in these operations, because in the current state of the hardware community, there's a variety of different distributions that may be coming out. And if we want to have some success for targeting these distributions, we want an initial result that allows us to target some set of these. Yep.
Maybe you could comment a little bit more on how realistic that those assumptions are for hardware. I mean, it seems they seem unreasonable for what the hardware is actually going to do.
So this is, I mean, frankly, I would agree. So the way that we've been developing this work is starting with the way we can build these results and do verification. We've been refining it while also refining the models that we have for how these distributions work. But I think good progress going forward is actually working with people like Louise and other people in this community to figure out what are the models that are consistent with the opportunities for making unreliable approximate hardware, and then mapping those back and deciding on how we can still verify properties of the software at large. Is that yeah, cool? So that gives us our hardware spec. Again, individual reliabilities for each of the operations that we have at hand. And now we can go ahead and modify our software, actually target this hardware. And the way this is going to look is that for any operation that I want to be unreliable in my program, I'm going to put a dot after it. This is going to communicate to Rely that this may execute unreliably on these unreliable execution units. I can also target these memories. So here, we've got, I may change, for example, these matrices to be stored in these unreliable memories. And the way we do this is by modifying our data type declarations to include an annotation of where this data is actually going to be allocated. Now, that gives us our hardware spec and our software spec. And now we can think about our software, our targeted software. Now we can think about our software specification itself. And the specification that we're going to have for interpolation is as follows. And we can step through this and let's go and make sense of this. And what we're going to do is we're going to modify, we're going to annotate our return value with the probability that we want for it to return the correct result. So here, the first way to start parsing this is to understand that the reliability of the output of a function is necessarily a function of the reliability of inputs, right? So if we're getting garbage in, we may get garbage out. And the way that we capture this is with this term, this R of xy source des term that we have in here. And what it does is it abstracts the joint reliability of this function's inputs on entry. So this is going to be the probability that all these particular values have the correct result on entry to the function. Now, to understand this and give this a semantics, it makes sense to think about what is the semantics of reliability that we're working with. Well, the way that we think about this is that we can imagine that on reliable hardware, there's one execution through some state space. And then on unreliable hardware, there are multiple executions. Some of them may end up in the same state. Some of them may end up in a different state. And reliability is going to be the probability that we reach the same state in our unreliable execution as we have in our reliable execution. Now, of course, to get these joint reliability terms, the way that we're going to define them is actually by refining this definition. So we're going to refine this definition, and here in this case, this R of the set of variables, it's just going to be the probability over this distribution of states that we have that only those variables listed, in this case x and y, have the correct values. So here, we're going to say so here for these two states that we have highlighted down at the bottom, right, for this reliability term where we just care about x and y, even though these two states differ on the value of z, they're same for x and y, so they're going to be same in terms of this reliability definition. They're the same on that subset of the program state. So now, given that definition of our reliability terms, we can actually go back and look again at the specification, now figure out what this 0.99 means. What this 0.99 is going to be, it's going to bound the degradation that we have while executing this function. So this reliability term, so the way you think about this is that when we call our function, we're going to start with some reliability of the inputs as captured by our reliability term. And then as we execute and we finish, we're going to finish with some reliability down here, and that's going to be bounded. The difference is going to be bounded by 0.99. So now this gives us the components that we need for doing verification of the program. So we've got our hardware spec, got our approximate implementation, and we also have our software specification. Now we can go ahead and build an analysis framework for doing this verification. And the way that we built this is what's called a precondition generator, sir. And what this means is that if there's some statement S and some postcondition Q that we want to be true at the end of S, what we're going to do is we're going to generate a P. And it's going to satisfy this kind of Hoare style notation that we saw before in the sense that if P holds before execution of S, then Q will hold afterwards. And the way we're going to do this is by starting at the end of the program, and then we're going to generate this P And then we're going to generate this P and check that it's valid, meaning it's equivalent to true. Because if it's valid, then we know that regardless of how we execute S, this function, function body or sequence of statements, we know that it's going to satisfy its specification. Right, and here in this case, this is going to be fully automatic, so this is going to be a static analysis. Now, of course, we got this Hoare notation on the slide, so we're thinking, oh, maybe we're going to cast this in terms of Hoare logic. But here, this isn't quite what we want to do because these P's and Q's that we want to express are going to be different. They're not going to be these values with variables in our programs. We're really interested in reliabilities. Right, and the way you can see that is by looking at how this reliability analysis, the generator would work. And again, it's going to start at the end of the program and work backwards to the top to generate this P. And the first postcondition that we're going to start with is that at the end of this, right, we want the reliability of our return value to be greater than, as a return value as computed, to be greater than the reliability that I have in my specification. And the way we're going to specify this is as follows. Right here, this looks a little complicated, but we can step through it. This is inequality, where on the left side, we have the reliability of our specification. This is verbatim of what we have in our specification at the top. Now, on the right side, what we're going to be interested in is the reliability of this specific executing this return statement, right? And that's going to be the probability. So this RD of val is going to be the probability that we read from val correctly, multiplied by the probability that our operation, this multiplication, executes correctly. And this is going to be multiplied by the probability of, or the reliability of the content stored in val itself, as was previously computed by the rest of our function. Now, this gives us kind of a flavor for what these inequalities look like. And in fact, when we're tracking these preconditions, they're actually a little bit, these preconditions and postconditions actually be more complicated in our analysis, in the sense that they're going to look something like this, where they're going to be this conjunction of inequalities, where each conjunct is actually going to capture some path through the program. We're coming up with some analysis for some path through the program. But as always, on the left side of this inequality in each conjunct, it's going to be reliability, our specification, just our specification. And then on the right side, we're going to have some reliability of the program state as has been computed along this path through the program. So now, when we take this, so now if we go and revisit our precondition generator, right? Our next step, we started at the end of the program, and now we're going to work backwards towards the beginning of the program. And the thing that we're going to do is we're going to expand this reliability of the content stored in val, right? Because in this previous step, this is where we're going to compute it, right? So here, when we do this expansion and we're working back to generate a new precondition, we're going to generate a precondition that looks as follows, right? And this initially looks a little scary, but the only thing that's changed here is what's been highlighted. So everything, again, left of the inequality specification, not modified. Then to the right, we still have the reliability of reading from val, reliability of our operation, and then now we've expanded the reliability of val with the reliability of this operation, this statement that we've executed here, where we have these 4 reads from source, so RD of source to the power 4, got these 3 additions of summing up our neighbors, the reliability of writing to val itself, and then we got the reliability of the data that we've accessed in this instruction or this statement itself. So now, that gives us our precondition here, and as we keep moving backwards through the program, we're going to keep generating these, but this is all reliable computation. So we're really just going to do these substitutions. And what we're going to get to is at the top, we're going to generate this final inequality, where if we generate or we verify that the inequality holds, that it's valid, we can be ensured that interpolation, when executed, is going to satisfy its specification. So now the way to parse this thing is, again, remember, left side of the inequality, completely unmodified. But on the right side, now we can see the breakdown of how we're computing this for this path, where we've got the reliability of our return, the reliability of our summary neighbors, and the reliability of the input dependencies explicitly just on this specific path of our computation.
What would it take to support unreliable control flow as well? I mean, I understand that you assumed, reliable instruction fatigue codes and so on. And so one could argue that just doing the data flow part, would not be enough for an instance because Remdal was law. But anyways, I'm just curious whether it would be possible at all
to
include the reliable control flow.
So reliable control flow in the sense of a data-dependent control flow based on some unreliable computation.
Well, that means that relaxing branch outcomes.
Oh yeah, actually.
Even jumping to random instructions potentially, essentially.
Yeah, no, actually, I mean, so if you've seen Margaret Martinosi's work in the past year in DATE, where they're looking on essentially these watchdog execution processes, I think that's a way of where, actually, can I talk about this at the end of the talk? Where, yeah, let's bring that up at the end of the talk. But I think you're right, and I think there are opportunities for doing that. So anyway, so back to this. This is the inequality that we want to check, that is valid, right? If we demonstrate that this inequality holds, then we actually know that our program satisfies its specification. And now to do this, the way that we're going to check this is the first step is we're going to take that hardware specification and substitute out these placeholders that we've had for our reliabilities, right? So this part that we have in orange, when we substitute that out, right, we're going to get this. Right? And this gives us our simplified inequality. Of course, it seems reasonable to kind of in some way check that. But remember again that in general, we've got these conjunctions, right? These conjunctions that are somewhat complicated in the sense that we really need to still understand what these R's mean if we want to figure out what it means to check this. And again, remember that when we define these R's, they were defined over the full joint reliability of these joint distributions of these executions in these states that we're reaching. And in fact, if you wanted to compute these, right, it'd just be intractable. Right? And even more concerning at this point, when we're trying to figure out where that we can pivot and target hardware directions, is that it would also be error distribution dependent. But, wait, oh, I think that was a sneeze. But what we found, right, is that you can sidestep this issue. And it's based on this observation. There's this observation that we made is that if you have the reliability of a set of variables, and I'm interested in the reliability of that set, and I add a new variable to that set, then the reliability of that new set is either the same or it's going to decrease, right? Our reliability isn't going to increase. And what that means is we can actually compare these inequalities or inequalities between reliability terms. So what we have down here at the bottom, for example, or if I know that the set of variables in this reliability term on the right side of my inequality is actually a subset of those on the left side of my inequality, then I actually demonstrate that this inequality, this relationship between the two reliability terms holds. So now based on this observation, it actually leads us to a nice checking algorithm, something that's going to be nice, efficient, and checkable. And what it is that each conjunct is going to be implied by a pair of constraints. So the first, we're going to have inequality over real closed fields. Again, it's going to be nice, checkable, tractable. And then we're also going to have inclusion tests over finite sets. Again, this is going to be efficient and also, importantly at this stage, error distribution agnostic. Now, when we take that and we map this and look on our inequality that we had from our interpolation example, what this seems, or what we can reason about this as, is this first inequality is going to be the reliability degradation that we have on this path for this particular conjunct. And then we're going to check that on this path that we've computed these data dependencies correctly, so they're consistent with the specification. Now, that wraps up how you'd verify the straight line piece of code that we have here. But anytime you see a programming languages, program analysis result, you should always ask, what about programs? Right? Because programs, they're complicated, right? They've got all these things going on. And in the interest of time, I'm not going to spend too much time on this. But what's happening here is if you think about functions, a really important thing is that we can do this modular verification in the sense that I can verify one component of my system, I can verify another component of my system, and I can compose them together, and the verification is still going to hold. In the case of loops, now the challenge that we have here is that the reliability of a loop carried, unreliably updated variable, right, is going to decrease monotonically in the number of iterations. So that means if we can finitely bound these loops, then we can put a finite bound on the decrease in reliability. But for unbounded loops, the conservative result is going to be 0. Now, I encourage you to ask questions at the end of the talk, actually, on how we can refine that, because we're finding that actually there are different patterns that these loops implement, and there may be appropriate different specifications or different analysis that we can do to get more precise results. Now, what's interesting is what happens with conditionals. And what's going on with conditionals here, and this isn't what Louise was looking at, and I'll address that later. But with conditionals, our way our analysis would work is that, imagine if we had this conditional test here, and we're computing the reliability of X on these in two different ways on these two different branches. Now, the way our analysis would work is, again, we're starting into the program. We have some precondition that we built up to this point. We're then going to split it off. We're going to go backwards through each of those conditions. We're going to put them up to the top. And we're going to conjoin them together. And this will give us a sound characterization of the reliability based on the non-determinism that we have here in this condition. But the thing to notice here is that if you ever see an analysis result where you're adding conjunctions at every single control flow condition, you should be concerned. Right? You should be concerned that there may be an exponential explosion in the size of these predicates, these preconditions that were generated based on the number of conditions that we have in here. But in this domain, there's an observation to be made. And the observation is that here, if you look at these two branches, right, there's actually an additional multiply on this side, on this right branch, as compared to this left branch. What that means is that this right branch is actually less reliable than this left branch. So what we can do and what our analysis does, and actually you can simplify this. You can throw away these constraints for the left side and essentially just track the least reliable paths that we have through the program. Because if we verify these least reliable paths, then of course we're going to have sound verification for any paths that are more reliable. Now this is actually really important. So we've taken this and applied it to a variety of different benchmarks from several different domains. And the verification results here are actually what's interesting, what's going on here. And here what we have on the slide is this right column is really what's important. So it's the number of conjuncts. And here is listed, the left subcolumn is the number of conjuncts if you don't do the simplification, so in this naive way, versus the number of conjuncts if you do this with this simplification. And what you can see is that what we're getting is this 4 orders of magnitude reduction in the size of these predicates, in the size of these preconditions, as we're doing our verification. And what's important here to realize is that although there may be a large number of paths through some particular program, there's typically a small number of least reliable paths. If we do verification for that, we can get some scalable verification that also holds for the variety of the paths that we have. Now that wraps up the way these components and the way Rely works, including its hardware spec, software specification, and the static analysis that we're doing. And this talks about reliability, right? And the probability that we're getting correct result. But when I talked initially about, and pitched this talk, I talked about bounding the difference in results. Right? And here, actually, reliability gives you a direction, gives you a vector actually thinking about bounding the results. Specifically, if we take something like our image scaling algorithm, where we have something like PSNR, which is a way of comparing the quality of 2 images, what reliability allows us to do actually bound the percentage of correct pixels that we have in our image. Using that percentage of correct pixels, we can actually then derive a lower bound on the quality of the image that we're going to see. Now, also, if you go back to the beginning of the talk, remember, kind of the key thing there is that we're going to verify these relations instead. Right? Instead of verifying during our standard verification, we're going to verify relationships between the original program and our relaxed program. And by building a logic that allows us to verify that, what it actually enables us to do is also write assertions, these relational assertions, where I could, for example, bound the difference between the result in the original program and the result in the relaxed program, and ensure that it's, for example, the difference is less than or equal to 2% of what I'd expect. So this is another directed way of specifying, verifying assertions about the difference between behaviors in my original program and my relaxed program. Now, what we've seen today, if you go back to the beginning of the talk, and with this last part, like all these things are together coming in to this system that we call Rely. We're on this bottom layer, we've got these different transformations, including unreliable hardware, and on the top we're doing this verification. And what's fun is the way I got into this research is that my advisor, I came from my grad school at midday, my advisor gave me a review for a paper for changing the semantics of programs from some other differences that had just been rejected. And the review said, I fear that techniques like this will bring on a new dark age in computer science, where we have these incomprehensible programs. And these techniques, this is that dark age. But what we've been able to do, and also including some of the work that's going on here, is that we're making directions towards building principled ways for reasoning about what these programs mean and being able to put bounds on the behaviors so we can actually get good results. Now, of course, this requires thinking about, pretty fundamentally, about what are the properties of these programs and how they behave and how we can verify them. And even going forward, there are a variety of future opportunities. So again, so that someone had pointed out before, we're thinking about what are the actual hardware models that are going to be consistent with where there are opportunities in the hardware side, and also that still support analysis. So this is definitely a currently active, very active area and direction for going to research. Like another very interesting problem to think about is that a lot of the work that's been going on in this community has been coming from the software and hardware communities. But approximation, this terminology approximation isn't new. Right? People in the algorithmic and theory communities and error analysis communities have been thinking about approximation for a long time. And there are guarantees that perhaps we'd also like to be able to specify and verify about our software. There's definitely opportunities there for dealing out how do you unify some of this reasoning. Now, I've also done a lot of different work on how you build safe and secure software traditionally. And even there are opportunities for applying approximations. In the sense that programs, they suffer from failures all the time. They'd be executing out to reference a null pointer. And while they would otherwise crash or throw an exception, what we can do is actually approximate. We could guess some value for that null pointer to reference. And this approximation, right, will allow the program to actually continue on executing acceptably. In fact, we've seen this in a variety of different benchmarks and a variety of different applications. And I think what people are connecting to and what we've had is that we've actually been able to get from these successes and kind of the intriguing craziness of this research, we've been able to get a lot of visibility not only in our immediate academic community, but also in our broader tech community as a whole. Now, what I think people are actually attaching to here is the fact that, as I pointed out before, this approximation, the concept of approximation in computer science in a variety of different fields isn't new, but it's been instantiated in a variety of different contexts here. And a good goal here, coming from the programming language standpoint, is how do we expose uncertainty as a first-class member in our programming languages so that we can actually exploit it to actually provide or actually utilize a lot of the different work that's been going on in a variety of different communities. So I think here, as more people are coming to computer science from backgrounds where uncertainty, and now increasingly computation are fundamental to the way they operate. There's a really good potential for having impact there and making these domains easier to map with abstractions that they have and that they're working with. Now, to wrap up, I just want to wrap up with my perspective and contributions. And the perspective is that there really are new opportunities here to improve software by incorporating approximation. Again, we've seen this performance, power consumption, but even for resilience in having programs that don't fail. But altering the behavior of programs, this is really tricky. It requires really careful reasoning, because this may jeopardize the safety or a variety of different properties that we really care about these software. But what I've talked today are some of the first systems for actually verifying quantitative properties we can quantify how different the behaviors in our programs are and verify that they'll still satisfy these properties. Well, that's the end of the talk, and I'd be very happy to take any additional questions.
So, follow up on Mark's question. I think what he was asking was, could you detect, catastrophic errors as opposed to just the average quality, right? But what I wanted to ask was, you taking a verification standpoint, you're trying to do static, as much as you can statically, right?
Mm-hmm.
So have you thought about how much could you move to dynamic world and still have savings? Something that you could do, some of this verification could be done dynamically that would probably give you stronger guarantees, would allow you to probably avoid things like extreme outliers and so on. But on the other hand, it has a challenge that it has to be cheap enough, right? So just whether you thought about doing some of this stuff.
No, and I think actually the best way to think about it, there are places where the static verification even falls over. And we had talked earlier about this with Dan, but with, for example, these loops that your bound is going to be 0, right? Well, you could actually count what your reliability is going to be as a function of number of iterations and have developers, for example, specify that, well, as long as it executes for this many iterations, I'm still within an acceptable bound. You could do that detection and check that and perhaps detect when you've gone outside of that bound or continue executing if you can. But I think is a very valid point. And I think what we are seeing right now is that there are avenues for applying traditional program analysis and verification. There are avenues for incorporating statistical methods. But there are still places where the reasoning falls over, and those are the places where we're finding that dynamic detection may be able to allow us to still have guarantees.
Thanks, Michael. And